Hello protostars! Today we'll be talking about one of the most fascinating objects of the universe, the black hole. Let's delve into the story of the formation of these cosmic bad guys. The moment a star enters into its main sequence phase, the tug of war between the gravity and the radiation pressure generated from the nuclear burning of its core starts. But when the nuclear fuel gets exhausted, the radiation pressure loses this tug of war and gravity starts to dominate. If the star has a smaller mass, anywhere between 0.4 to 30 times the mass of the Sun, then degeneracy pressure comes to its rescue and stops its collapse further, and the star becomes a neutron star or a white dwarf. Anyway, the degeneracy pressure is a topic of another video. Let's come back to the formation of the black hole. So, when the star is more massive than the 30 times the mass of the Sun, gravity starts dominating so much that it squeezes the entire material of the star into a single point. But wait, why the images we see on the internet looks like black hole has a finite size? To understand this, we need to understand the concept of event horizon. When you throw a ball in the air, it comes back to you after reaching a certain height. But when you throw this ball at a velocity of 11.2 km per second, then it escapes the Earth's gravity and doesn't come back. Similarly, if any object passes near the Earth with a velocity less than 11.2 km per second, it gets trapped in the Earth's gravity and never leaves the surface of the Earth. This 11.2 km per second velocity is called the escape velocity of Earth and can be calculated from this formula. The velocity of light is the maximum velocity achievable in the nature. Now imagine an object so massive that even light cannot escape its gravity. What will be the radius of this region beyond which the light won't be able to escape this object's gravity? We can calculate the radius of this region by rearranging the escape velocities formula. This radius is called the event horizon of this black hole. We are only able to see an object when light gets reflected from its surface. But as the light cannot escape from the event horizon, the region beyond the event horizon is totally invisible. This is why we cannot detect any light all the way up to event horizon from the center of the black hole. Due to concentration of huge mass in such a small region, black hole has insane gravitational pull. It eats objects like stars and planets like we eat dinner. When any object comes near the black hole, it gets ripped apart. Material doesn't fall directly onto the surface of the black hole in a straight line. It is because the material has some angular momentum left, and angular momentum is always conserved. The ripped apart material makes a swirling motion around the black hole and forms a disk. This disk is called accretion disk. Due to the internal friction of this ripped apart material on the disk, accretion disk gets heated up to a very high temperature and it shines very bright. Generally, it is the accretion disk which gets detected and it helps detecting the black hole itself. There are other effects which help detecting a black hole like gravitational lensing and gravitational waves. If you like the content, hit like button and subscribe the channel Astro Guy Rashid. I will meet you in the next part of this video where I will be talking about different categories of black hole and what is the effect of this black hole on our universe.